Hello viewers, you must be familiar with what the basic proportionality theorem is. Let us quickly recall what basic proportionality theorem is. The basic proportionality theorem was given to us by a Greek mathematician named after Thales. Now according to Thales' theorem, if A, B, C is a triangle and we draw a line DE parallel to BC, then it will divide the sides AB and AC proportionally. What does that mean? Let us see that. Now here DE is parallel to BC. So according to Thales' theorem, AD upon DB will be equal to AE upon EC. Now this being a equality, I can add 1 to both sides, and on adding 1 we get which on simplification gives AD plus DB upon DB equals AE plus EC upon EC, and AD plus DB is nothing else but AB upon DB, that is equal to AE plus EC, that is AC upon EC. And now we shall be making use of this basic proportionality theorem in having some important constructions. The very first construction is that if we are provided with a straight line and we have to divide it in a given ratio, then how this Thales theorem is helpful to us, let us see that. Here in the problem, divide a line AB 14 centimeters internally in the ratio of 3:4. To divide the line AB, which is 14 centimeters in length, first we shall draw a line which is 14 centimeters naming this line as AB. After that, we shall make at A any convenient acute angle. After having done this, we will divide this line in 7 equal parts, which is nothing else but the sum of the ratio, that is 3 and 4. One, 2, 3, 4, 5, 6 and 7. Let us name these. This is 1, 2, 3, 4, 5, 6, 7. Join the 7 number to the point B . And we name this point as C. After that, we will have to draw a line parallel to BC at this point. To do that, we will be making the concept of parallel lines, that is the lines are parallel if the corresponding angles are equal. So, for that purpose we will make an angle at number 3 equal to the angle over here. Measuring this angle, name this point as D and this as E. Here the line DE is parallel to line BC because we have made this angle equal to this angle, and these are nothing else but corresponding angles. Now, if you happen to recall the basic proportionality theorem, in the basic proportionality theorem it is stated that in a triangle, if a line is drawn parallel to any side of a triangle, here we have drawn this line DE parallel to side BC of a triangle. So, this line will divide these two sides in the same ratio, that is AE upon EC is equal to AD upon DB. Now, how much is the length AE? AE is 3 parts and EC is 4 parts. So, 3 upon 4 equals AD upon DB. So, we can see that the ratio of the length AD is to DB is nothing else but 3 is to 4. Let us verify this by actually measuring the lengths AD and DB. The length AD is 6 centimeters, AD by actual measurement is 6 centimeters, and let us see the length DB, this is 8 centimeters. Taking the ratio of these two lengths, that is AD is to DB, that is equal to 6 is to 8, which on simplification gives us 3 is to 4. So, here is the one concept where we divided the line internally in a given ratio, and when the point which divides the line internally in a given ratio, that always lies between the endpoints of the given line. But it may not always be the case. We may have to divide the line externally in a particular given ratio. Let us see how we do that. Here, divide a line segment which is AB 14 centimeters long externally in the ratio of 5 is to 2. Now, the same way, first I will draw a convenient angle at A. Remember, this angle should be acute. Then we cut 5 parts on this, 1, 2, 3, 4, 5. At B, I will draw a line which is parallel to A5. To draw a line parallel to A5, first I draw an arc, and the same arc we draw here, extending this line AB The measure of this angle is this much, and we will cut off the same angle from there. So, here we see that this line is now parallel to this line, and with the same units, that is the parts which I had cut over there, this I will cut off two parts, this is 1 and this is 2. One, 2, joining 5 and 2, we get this point E, let us say, which divides AB externally in the ratio of 5:2. Let us use the BPT to say whether it is actually 5:2 or not. Here now this line is parallel to this line. So, by basic proportionality theorem, AB upon BE, this has to be equal to A5 upon B2. Now, since A5 is 5 parts and B2 is 2 parts, so the ratio becomes 5:2. So, this is once again how we make use of the similarity and the basic proportionality theorem to divide a line segment externally in a particular ratio. But it is not only the line segments which are to be divided. At times we have to draw a triangle which is smaller in size to that of a given triangle. Let us say here in this triangle ABC, I have to draw another triangle which is 3/5 of the corresponding sides of triangle ABC. To do that, once again we will divide the line segment BC into 5 equal parts. So, here is the line first we draw, then we mark 5 points on this, 1, 2, 3, 4 and 5. Join this 1, 2, 3, 4, 5, join this fifth part to C. And at point 3, we have to draw a line parallel to 5C, and for that we shall follow once again the same procedure, that is, I will be drawing corresponding angles equal. Let us see the measure of this angle. These two arcs, this arc and this arc, intersect each other at point over here. So, if I name this point as B dash, then clearly BB dash is 3/5 of BC. Now, at point B, I will once again draw a line parallel to AC, and for that we shall follow once again the same procedure of making corresponding angles equal. Joining B dash to the point of intersection of the two arcs, we get a point A dash. Now, the triangle A dash B B dash is exactly similar to triangle ABC, but its sides will be 3/5 of the corresponding sides of the triangle A, B and C. Let us verify one of these sides. Now, here BC is 15 centimeters and BB dash is 9 centimeters. So, you can see BB dash is 3/5 of 15th. Similarly, if you happen to see this side, AB is 12.5 and this is A dash B 7.5. So, here we see that A dash B is 3/5 of AB, and similarly we can verify for this here AC is it's 10 centimeters and A dash B dash is 6 centimeters. So, here we see that BB dash is 3/5 of 15, A dash B is 3/5 of 12.5 and A dash B dash is 3/5 of 10 centimeters, that is 6 centimeters. So, this is how we make use of the basic proportionality theorem and similarity in constructing a triangle which is having a ratio to the given triangle. Besides triangles, it is possible for us to construct a quadrilateral whose sides are proportional to the given quadrilateral. Let us see a problem. Here construct a quadrilateral similar to a given quadrilateral PQRS with its sides 5/7 of the corresponding sides of PQRS. Now, to construct this, what we will do? We will have the required quadrilateral which is PQRS, P, Q, R and S, and firstly we shall join its diagonal QS. After joining the diagonal QS, we will divide it into the required parts as asked for. We will draw any acute angle over here and cut off 7 points on this. 1, 2, 3, 4, 5, 6 and 7. Joining this 7 point to S, this is the 7th point, and from the 5th point we will draw a line parallel to S7. The measure of this angle is this much, cutting off that angle from there. So, let us name this point as S dash. Now, Q S dash is 5/7 of Q S. From S, I will draw a line parallel to P S. Naming this point as P dash. And from the same point S, I will draw a line parallel to S R. So, here is a point where the arcs are cutting. Let us name this point as R dash. So, here the quadrilateral Q P dash S dash R dash is similar to the quadrilateral Q P S and R. Now, besides triangles and quadrilaters, it is possible for us to construct a polygon similar to the given polygon, that you can try yourself at your place. Now, we take up another case where we will be finding the mean proportional between the two given numbers. The problem is, find a mean proportion between 10 centimeters and 6.4 centimeters. First, we shall draw a line which is equal to the sum of these two lengths, that is 10 plus 6.4 centimeters, that will be 16.4 centimeters. So, here we draw a line which is 16.4, and mark on this line the first length which is 10 centimeters. So, here is A, B, and this is the point C. So, AC clearly here is 10 centimeters and CB is 6.4 centimeters. So, firstly we shall bisect this line AB, that is, we shall be getting the midpoint of the line AB, and for that once again we make use of compass. Opening it a little more than half, we will draw an arc up and an arc down, and from the end A we will draw another arc these two arcs cut at these points. On joining these, we get the midpoint of AB. Let this point be named as F. Now, taking F as center and radius equal to FA, which obviously will be equal to FB, we will draw a semicircle. And at the point C, which is at a distance of 10 centimeters from the point A, we will draw a right angle. 60s, that is 120, and bisecting 60 and 120 we get an angle of 90 degrees. This CD is the mean proportion between AC, that is 10 centimeters, and CB, that is 6.4 centimeters. Let us see how much is the length of CD. CD is 8 centimeters. Now, let us apply similarity to see is it 8 centimeters or not. For that purpose, we will join AD and BD. Now, triangle CAD is similar to triangle CDB, because these two triangles are similar. So, therefore, CA upon CD will be equal to CD upon CB. If we cross multiply them, we get CD square equals CA times CB. Now, CA is nothing else but 10 centimeters into CB is 6.4, and that will be equal to 64, and therefore, CD is root of 64, which is 8 centimeters, and that we have verified by actually measuring it. So, this is the way how we find the mean proportional between given two numbers. And that is all for the day. I hope you must have gathered how to make use of similarity and the basic proportionality theorem to construct some of these constructions.